This is Lab 7, Part 3 of the Magnetic Field Lab. This part deals with measuring the magnetic field strength, actually mapping out a magnetic field. In order to do that, we're going to take and use a giant Helmholtz coil, okay, to create a magnetic field. Use our power supply once again, Pascal power supply, and we need, of course, to use a ammeter in order to know the current, so we can calculate the strength of the magnetic field. In order to make these measurements, we'll be using this device here. This is a vernier sensor that we use with lab probe, logger probe here. So the sensor is connected to the lab probe, which is, of course, connected to the hard drive of our computer, and will record the data onto the hard drive. The sensor is within this tube. It detects magnetic field lines, and there's a white dot printed on the tip of this tube. The normal of this dot is to be parallel to the magnetic field lines. So when you have a Helmholtz coil like this, magnetic field lines are run parallel to the axis of the Helmholtz coil. Okay, and the positive direction of that is determined once again by the right-hand rule. So you can see where my current is coming in. It comes into this side here, and by inspection, I can see that it's connected to a wire here that's running in this direction. So by the right-hand rule, as I curve my fingers in the direction of the curve of the wire, my thumb points in the positive direction of the magnetic field. So this is the positive direction. This is the negative direction. Okay. So I've got the circuit hooked up, and I can take and turn this on, and we're told to create a 0.4 amp reading. And I know you can't see the reading here, but it's less than 0.4. So let me turn that up to 0.4. And if we put in 0.4 amps, the number of turns, these giant Helmholtz coils have 124 turns or windings in each coil. There's two sets of coils, but there's 124 in each of these. So N is 124. I is the radius of this. So take your meter stick and measure the diameter, and then half that to get the radius. Okay. Mu sub O is that constant we spoke of earlier, 4 pi times 10 to the minus 7th. And at this point, we have to take and calibrate our sensors. So let me turn the camera to, oops. Computer here. Start with, you come up to this icon, click on it, the little Lab Pro icon. And I'm hooked up in channel 1, so we'll choose channel 1. And from the list, we go down and choose magnetic field sensor. Click on the corner of that and say calibrate. Rings up and says a window. We'll choose calibrate now. And to the right of it, it shows units. Now, it's in milliteslas, and I'm opposed to that. I just want to use SI units directly. So I'm just going to make that teslas. I eliminate the M in front of the T there. So instead of MT, it just says T now for teslas. And down here, these boxes have changed to T's also, the units have. Now, in order to calculate or to calibrate, I have to input what the B field is into this number in that box, while simultaneously holding my sensor inside the Helmholtz coil. So I'm going to hold this here, have it aligned so that the normal, okay, is parallel to the axis of the coil. And let me type in a number here, the magnetic field strength that I calculated for 0.4 amps. Hold it steady. That is, hold the sensor steady in place in the middle of the Helmholtz coil and say keep. Okay, I've done that. Now over here, oh, I should say, now it's asking me to put in a second reading, and the second reading is going to be the opposite direction. So I've taken my sensor here and rotated 180 degrees, and now it's pointing in the opposite direction, pointing in this direction now instead of this. Okay, now pointing in this direction. And into that window, that secondary window, second window up here, I have to put in a negative sign and then put in my magnetic field strength and say keep that. All the time, all the while, I've got to have to make sure before I say keep that my sensor is positioned correctly. I haven't moved it. So I say keep. All right. And once I've said keep, I can say done, and it's done. And although you can't see it very easily, let's okay, so you can see the reading here with the sensors picking up. And if I move my sensor, I'm just merely rotating it. You can see that the values are changing. So here it's aligned with the magnetic field. It's a positive quantity in the thousands of Teslas, you know. And if I rotate it 180 degrees, I get the negative quantity, this time in the thousands of Teslas. If I take it out of the magnetic field, you can see that it goes down to some minimal value. It doesn't go to zero because there are magnetic field lines in this room. For one thing, the Earth's magnetic field permeates this room. And then any device that has currents flowing through it is probably creating a magnetic field. All right. If you take these sensors and hold them up to any of these transformers, you'll get a reading. You'll pick up that. And I'm sure if you held it to the back of these computer screens where the computers are, you'll get a reading. And if you hold it up next to the power supply, you should get a reading. So what you're going to do here, set this up. We've got a Helmholtz coil with a known magnetic field in it. And we want you to take your sensor, hold it steady, and take data, and then rotate it 90 degrees. So now this dot, the normal is pointing straight upward, and take data. Rotate it again another 90 degrees. The normal dot is pointed in this direction. Take data. Rotate another 90 degrees such that it's pointed downward. Take data. Then return the original position pointed in the original positive direction. And if you do that, well, let's quickly do it and see what it looks like. I'm going to set this up for a data collection of, let's say 40 seconds. And I'm going to take 50 samples per second. And I am going to hold my sensor inside the Helmholtz coil in the center, and I'll say take data. So it's taking some data. I'm rotating it 90 degrees. It's taking some more data. I'm rotating it again another 90 degrees. It's taking data. Rotate it another 90 degrees. It's taking data. and rotating back. Once again, it's taking it. And now I'm taking it outside of the magnetic field and laying it down. Back on. Okay, next to the power supply, I can detect something. Let me stop it here. Now let me just say that when you get a flat line like this, that usually indicates that you didn't calibrate it correctly. And I might have mistyped my numbers in. These lines here should look more like this, kind of jagged. Okay. And let me show you an example of what I got earlier. So this is what I achieved earlier when I did this. And so here's where I was aligned with the magnetic field. Here is where I was 90 degrees to it. Here was in opposite direction. So this is a zero line. So this is a negative of that. And then I aligned it in the opposite direction. Notice that this is slightly above zero and this is slightly below zero. And once again, that's because they are there is some magnetic field strength in this room. And it was detecting it. And my direction of my detector was in different directions. So that's why it's one's positive, one's negative. Then finally, I returned it to the original position again. And this is what you should do. I took, and in order to find out what some of these values were, I just selected part of the data, went up here to analyze, chose statistics, and you can see there's a mean value given in the statistics box here, and that's what the average of all these values in my selection is. Okay, so I got a mean value in this case of negative 0.000341. Yeah, so I definitely inputted, I must have mistyped when I put the numbers in because this should be, that is not the field strength of the magnetic field in the Helmholtz coil. Okay, so you're going to do that part, and then you're going to do, pardon me, start over again. And you're also going to take and map the magnetic field strength along the axis. Now here these wooden boxes come in handy because they're the right height to lay a meter stick on. And you are going to take your, sensor and start here at the center and move along the meter stick taking data. Okay. And I found the easiest way to do this is I just held my sensor here in the center, held it steady for a few seconds, and I gave it a twist. And that causes the recording in the logger probe to spike. And then I would move it, say 3 centimeters, hold it still, take data, twist it again, causing the data to spike, and then move on. And so if I did it every 3 or 5 centimeters, kept that constant, constant intervals, then I would end up with a graph that I could interpret easily. So let me go ahead and take some data real quick. I'm going to hold this in the center. Like I said, I'm taking data and I'm twisting it. And then I'm moving it, say, 5 centimeters, twisting it again. Moving it 5 centimeters, twisting it again. Moving it 5 centimeters, twisting it again. And you can see what I've created here is a graph where I took some data and twisted it. Okay, license and cause a spike. Now, like I said, this is out of calibration, but I've got some data here. I twisted it. 5 centimeters later, I took some more data, twisted it, took some more data, and I twisted it, held it steady. Well, I tried to hold it steady, but apparently, when you're moving it, it's bouncing around. But I held it steady here, and I twisted it, and then I moved it, and then try to hold it steady here, and twisted it, and moved it again, held it steady, twisted it, and these spikes should be every 3 or 5 centimeters, whatever you held it to be. And somewhere I will show you I'll show you an example of this data that I've taken, and this is one of them. Okay, so in this case here, I had the sensors calibrated correctly, and I twisted I think every 5 centimeters, and I got this. And what you can do is what I did before, select an area, do statistics on it, get the average value, or just try to read it off of your graph here in Logger Pro. So, if this here is the value, you can place your cursor right there, and you can see on the XY values down here what that Y value is. And then you can move it over here, the next one, and record that Y value. Or you can do what I did. But once you get all these Y values and know that they are so many centimeters apart, you'll be able to create a graph showing the magnetic field strength versus distance. And so you'll get something that looks like this. Here in the center of the Helmholtz coil, it should be a constant magnetic field strength. And then as you move outside of the Helmholtz coil, it starts to fall off. And that reason is because these Helmholtz coils, like this, they create a very uniform magnetic field within the coils themselves. So in this area here, between the two hoops, you have magnetic field lines that are parallel to each other, and they occupy pretty much the whole volume inside here. Now, as they come through, they take and they come out and then start to bend around and come back in this side. As they come out and meet here, or they come out and meet up here. But within here, the magnetic field lines are constant, they're equally spaced, and it's a constant magnetic field. And that's what you want to have at your as a measuring tool. Now, the last thing you're going to do is you want to take these devices here and measure the pulse strength of these things. As I say, let's say place them so that they're a distance apart from them. Let's say 5 centimeters, and record what that number is. So if I were to come back to my computer here and hold my sensor, say 5 centimeters above it, I can see I'm reading some number, okay, and I record that. And then I'm going to take and record in case of the other magnet and hold it the same distance and record that number. Those two numbers should be the same. They may not, but they should be. After all, we did assume they were the same in part one. But these are magnets, and sometimes through use, they lose some of their magnetism, and they may not use them uniformly the same, right? And I believe that is the lab. Contact me if you have any questions.